Hello everyone, welcome back to the channel. In today's session, we will explore another important topic in microcontroller programming. Lecture 8, Logical Instructions in the 8051 microcontroller. Today's topic of the day focuses on how the microcontroller performs logical operations such as AND, OR, XOR, NOT and bit manipulation. In this lecture, we will cover four key areas. First of all, the syntax of logical instructions. We will learn how instructions like ANL, that is the AND logic, ORL, that is the OR logic, XRL, that is the XOR logic, CPL, that is the complement. This is for NOT logic. Are written and used in programs, right? Second thing, the working of logical instructions. We will understand how these instructions operate on bits and how they modify data inside registers and memory. Third thing, we will go through examples of the logical instructions. You will see practical instruction, examples and how they work step by step. Finally, we will discuss the applications of logical instructions such as masking, setting, clearing bits, data processing, and control operations in embedded systems. By the end of this lecture, you will clearly understand how logical operations are used to manipulate data at the bit level, which is essential for efficient programming in microcontrollers. So let's get started. Right? Today's lecture, that is the logical instructions. First of all, we will see the syntax of logical instructions, working of logical instructions, examples of logical instructions, applications of logical instructions. Right? We will see all these things in the detail. Right? Now, we can see here the recap on the arithmetic instructions. We have already seen these things. Syntax of arithmetic instructions, working of arithmetic instructions, examples of arithmetic instructions, applications of arithmetic instructions. We have already seen in the previous lecture. Now, we will see after the lecture of this presentation, right? First of all, use instructions to perform bitwise operations in 8051 assembly. Second thing, apply bit manipulation instructions to control hardware ports and flags, right? Next thing, write logical operations for masking, toggling and conditional control in programs. Right? Now we can start one by one. From here you can see. Right? First instruction. First instruction, that is the AND logic. ANL, that is the registers. In this, we will see the example of here ANL, that is the AND logic, A accumulator, comma R0, R2. Okay, so we can execute this instruction. right? This instruction is a one byte instruction. The execution of this instruction is required one machine cycle, right? We can use also the opcode, right? 52. If we can put the 52 opcode in the hexadecimal in kit, right? Microcontroller kit. So this 52 opcode just like we have of this type. Okay. Okay, how to just work of this logic? So we can take a small example, right? Okay, now we can take a small example here, right? Yes, you see one by one. A, that is the, suppose we have the two digit or three digit we can take, right? Suppose we can take a digit here 0 0 0 1, right? And R2, this R2 we have, right? So 1 0 0 0 1, right? In this, suppose we have the data in this way, right? After the execution of this instruction, what is the result, right? And result will store in the accumulator after the execution of this instruction. So the AND logic here fulfill this condition, the 1 into 1, that is the 1, right? 0 into 0, that is 0, 0 into 0, that is 0, 0 into 1, that is 0. This is the one value come here in this. This is the answer of AND logic, right? In the similar way, we can calculate this AND logic in the immediate form, right? So we can use here, this is the immediate number, right? A, that is the sum value, suppose in the similar way, right? 5 value also included in this, so we can just multiply of these bits and one by one. So answer will store in the accumulator, right? This instruction is the 2 byte instructions and execution time for this instruction is one machine cycle, right? Opcode of this instruction is 5455H, right? In the same way, we can use here the ORL, that is the OR logic, right here. To OR logic in the form of the registers, so we can use here the registers, destination register, source register, right? So some values are given here, the content of this register, content of this register. Follow the operation of the OR logic and final answer will come and store in this accumulator. Okay, you can calculate. Now this instruction is a one byte instruction, right? The execution time for this instruction is 1. Opcode, you also remember this thing if required, right? 43. So not a 43, you just read in this way 43H. Okay. Okay. Now we can use here the another instruction or logic immediate, right? Here we are using the immediate. A, that is the accumulator. Accumulator must be there here in the destination part. Otherwise, this instruction will provide the error. Right? This is the immediate value, means fixed value or constant value. Right? Now the operation of the OR logic is occur here. Right? And answer will store in the accumulator. Right? For this purpose, this is a 2 byte instruction or one machine cycle is required for execution of this. This is the opcode and a 440FH, right? In the similar way, we can use here the XOR logic, right? Here this one. Now we can use here the XOR logic, XRL A comma R4, right? The content of the R4 and content of the A, right? So finally the XOR logic will execute here and final answer will come in the accumulator, right? For this instruction, this instruction is a one byte instruction, right? And one machine cycle is required for execution of this instruction. 65H, that is the opcode of this instruction. In the similar way, we come here, right, where cursor is available. I think okay, now okay, CPL, that is the complement, okay, accumulator. Suppose this value, right, complement, some value 0 is there, this will complement 0, that is 1, 1, that is 0, right? Result will come in the accumulator, right? This instruction is a one byte instruction. The machine cycle for this instruction is 1, right? And opcode of this instruction is F4. Noted? Okay. CPL bit. Okay, this one. Bit is nothing but port pin. है ना? This is the one pin we consider here. Right? CPL P1.0. Right? This is the first pin of the port P1. Right? This is the just 2 byte instruction, है ना? And for this execution, 2 machine cycles are required. Okay. Opcode of this instruction is B290. Right? Remember? Okay. Just the CPL P1.0 means suppose one value is given at this port, right, P1.0 at this pin, right? This complement instruction, this is just a toggle of this. 1 converted in 0, 0 converted into 1, right? In the same way, we can use here the CLR, that is the clear accumulator, right? Suppose some values are given in the accumulator. So this clear instruction just clear all the values. Now not value is given in the accumulator. 0, 0, 0 or values are given in the accumulator by using this clear instruction. This instruction is a one byte instruction, right? The execution of this instruction is required one machine cycle. The opcode, that is the E4, right? Noted? Okay. Next thing, this is the clear CLR bit. Okay. This is nothing but P3.2, pin number 2, pin number 3 of the port 3. Okay. So clear pin, this pin. Okay. Okay. Suppose any values already here in this pin. So by using this instruction, this should be the 0 now. This instruction is a 2 byte instruction. The execution of this instruction is required 2 machine cycle. Right? Opcode of this instruction is C2B2. Just a remember of this opcode, because this is not just a series, this is just a code given by the manufacturer. Okay, so you can just follow this table, right? Now next thing is available here, the set bit. Okay, set bit P2.0, that is the example, means this value already 0 here. Now this will set of this pin, means this is the high of this pin, right, after the set bit. Okay, this instruction is a 2-byte instruction. For this execution, for this instruction execution time, that is the 2 machine cycles are required. Okay, opcode D297, that is the opcode for this instruction. Right? Right. Now we can move for this logical instructions. Some more instructions also given here, you see. That is the RL. RL is nothing but rotate left. If we want to rotate the bits, right? So in the left, rotate left, that is use this instruction RLA. Okay. This instruction is a 1-byte instruction. The execution of this instruction is 1 machine cycle. Right. Opcode of this instruction is 23 has. Right. H. Okay. In the same way, RLC rotate left throw carry, right? So we can use this instruction RLCA, right? We will see some example in the future slides. You just read out the logic, or we can understand the logic from here, right? Just a comparative things available in the tables, right? RLC, that is the rotate left throw carry accumulator, right? This instruction is a 1-byte instruction, or the execution for this instruction execution is 1 machine cycle is required. Okay. Opcode, that is the 33H. Okay. Rotate right. So RR instruction we can use RRA. Right. This instruction is a 1-byte instruction. The one machine cycle is required for this execution. Right. Next thing, the opcode 03H. Suppose we want to use this code. So this is just like a rotate right accumulator. Right. Rotate right throw carry. We can use this instruction RRCA. Right. This instruction is a 1-byte instruction. 1 machine cycle is required for this execution of this instruction. 13H, that is the opcode of this instruction. Next instruction is a nibble swap. Okay, this one. So swap, nibble, swap, right? This is the swap A, right? This is the 1-byte instruction. The 1 machine cycle is required for this execution of this instruction. The C4, that is the opcode of this instruction. Noted? Okay. Now we can move for the logical instructions one by one. In the similar way, we can put here the small example, just wait, and we can move for the next slide. We can take important things, logical and. The syntax of this instruction is ANL, A comma source, right? Source is nothing but R, that is the register, memory, immediate number. Anything we can put here, we can use, right? Operation of this instruction performs bitwise logical and operation between accumulator and source operand, right? And the result is placed in the accumulator. We have seen the previous slide, and during the comparison of the instructions, I have just calculate all the things, right, with the example. A and source, right? A and source. A, that is this one, right? And this is the logic. This logic we are using here. Source, this one. Anything we can use here, right? After the execution of this, the result of this will come in the accumulator here. We can take a small example here. ANL, A comma has 1 to H, ANL AB, ANL A comma 50H, ANL A at the rate at the comma at the rate R1 RI. We can put here R0 or R1, any one we can use, right? A, that is the 12, we can consider here this is the binary number of this hexadecimal number. B, that is the 0F, right? This one, this is the binary number, right? The result of this result will come in the accumulator A. So how to come this result? Because the logic here use the AND logic. AND logic is nothing but multiply of the bits, and bit by bit. So here you see this is the 0 multiply 1, that is 0. 1 into 1, that is 1, 0 into 0 into 1, 0, 0 into 1, 0, 1 into 0, 0, 0 into 0, 0, 0 into 0, 0, 0 into 0, 0, right? This is the result. Result in the hexadecimal is 0 to B. This is the binary form, but we can convert in the hexadecimal again, right? We can use this value, we can store in the accumulator, right? A bit can be masked, that is the reset, by ending with 0, right? This is the mask purpose, right? The application of this AND logic. Okay, now we can use the just OR logic, and a similar thing we can use here. Just you can try, right? A bit can be set to only to 1 by ORing with 1, right? In this case we can take an example here. Similar thing we have seen already in the previous, right? This is the OR logic, right? Here so we can just add and add this values by using the OR. So 0 plus 1 1, 1 plus 1 1, 0 plus 1 1, 0 plus 1 1, 1 plus 0 1, 0 0 0, 0 0 0, 0 0 0, right? This is the result. This result we can convert in the hexadecimal number. This value we can store in the accumulator, right? This similar thing already we have discussed, right? Next thing, the XOR logic, right? This one. X1 logic also, you can see here a bit can be complemented by XORing with 1, right? Here you see, right? We can take a small example here, 1 2, we can take here the binary number of this hexadecimal number as 0F, that is the binary number. We can just XOR logic, basically they provide if the both bits are 1, they produce the 0 output, remember, right? So 0 1 1, 1 1, and a 1 1 they produce the 0. If any just digit is 1, the produce the value 1, but both digits are the same, they produce the value as 0, right? So different values are given, that means they produce the 1. So this is the thing available, you can just use or just XOR logic, right? You can implement here. We can clear any bit by performing XOR with same bit. Clear accumulator, right? First of all, we can see here the syntax, clear A. The operation of the syntax is this instruction clears accumulator contents, okay? A00, that is the A you see here, right? We can take example, a small example here. A equal to 1, 2, right? This is the hexadecimal value. Now we want to clear A. Some values are given here, but after the instruction, using this instruction, right? They produce the always 0, 0. This value may be, any value can be here, but after this execution of this instruction, they produce the 0, 0 value. Complement accumulator CPL syntax, that is the CPL A. Operation, the CPL instructions logically inverts each bit of the accumulator and store the result back in the accumulator, right? You see here we can use just this sign, right, for the not purpose, right? So this is the thing, resist will come in the accumulator, right? We can take example here, A equal to 5, 5, right? A equal to 5, 5, this value is given. But after complement of this thing, the result will come in this way, right? You see here the complement of this A, they produce the value in this way, just a reverse of this value, 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1. Okay, the final result is AAH, right? Now we will see here the swap instruction, right? What is the use of this instruction? You see here, exchange nibbles of the accumulator, right? Just swapping है ना, by using this instruction. Operation, the swap instruction exchanges the lower and higher nibbles within the accumulator, right? A equal to 4 to H, right? This is A equal to this value already given, right? But we want to use this instruction. So you see here, this is the swapping. This number will come in this side, this number will come in this side. This is totally swap 2, 4, right? Now, okay, now we come on the rotate right. You see here, this is the very simple. Just you see, है ना? This is the just a digit, है ना? This one. B1, B2, V3, V4, V5, V6. है ना? This is starting, that is V0. V0 is nothing but least significant bit. This is the most significant bit. Okay. So you can see this is the arrow. Arrow just showing the right. है ना? Left to right, we can say, right? So now the rotate right, we can't, we want to shift this digit, come here, right? This digit come here, and this digit come here, 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 this digit come here. We can take a small example here, you can see, right? This is the 4 2 value, है ना? This one. This value we can represent here, right? This one. So this value come here, है ना? In this way we can just take of this. We can try, just wait, rotate the things. Okay, where is available? Yes, this is the number basically. Now we want to shift, है ना? So this one shifted here, this location, है ना? This value come here, 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 this value come here. In this way the result will come. Suppose we want to convert this result in the hexadecimal, so that is the 21H. Okay? Okay. Now we can move for the next. See here, rotate right throw carry, right? Rotate right throw carry, you can see, है ना? This is the very simple. You just see. This is the similar we have seen in the previous slide. This is the same thing. Only change the carry is given here. Carry is already given here. So now we want to shift. Basically, this carry also included in this number. Now this number is the 9 numbers. Remember, right? Now this values come here in place of the carry. This carry shifted here, this value come here, this value come here, this value come here. In this way we can take a small example here, right? This is the 4-2 value, this one, but carry also given. This carry shifted here, right? This one. So this value come here in this. This is the 0. Now this value is shifted here in place of the carry, right? This value come here, right? This one, this one, this one, this one, this one. In this way we can just represent. This is the very easy. Okay, now rotate left, right? Syntax is given here. You see, this is also the very easy thing. Rotate left. Now we can change of this. Now from right to left we want to shift, है ना? In this way. So this value come here in place of the LSB. This value come here, 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 right? You can see here we can take example. This one 4-2 we consider, right? After execution of this you see, right? We want to shift in the rotate left, okay? So left means from right to left, this way, in this way, right? This one, right? So this one thing, this value will come here, this one. This shifted here, this shifted here, this shifted here, this shifted here, this shifted. In this way, the shifting will come here. Now we can just go through this, the same pattern, right? Rotate left, throw carry. Right, this is the similar thing, only carry we can added here, right? This value come here in the place of carry, this carry come here in the place of LSB. All bits are shifted from right to left, and one shifted. So this is the thing, this already done, right? This is the similar thing. Now we come, this is the Boolean, or we can say the bit manipulation instructions. Only one bit. Here we can change clear C, set bit C. This is the just related to the carry, right? So just see the things. Okay, set bit carry, complement C, clear bit, set bit, right? Here the CPL bit, ANL C, comma bit, ANL C, comma this bit, है ना, slash bit, ORL C, comma bit, ORL C, comma, this is just like a symbol, right? This one represent the bit complement of this, है ना, this one. Move C, comma bit, move bit, comma C, right? So we can use this bitwise also. Now we come on the summary of this presentation. We discuss following key topics: syntax of logical instructions, working of logical instructions, examples of logical instructions, applications of logical instructions, right? Now we complete this part and we will discuss in the next lecture. We will learn how the 8051 makes decisions and branches execution using conditional control transfer instructions, right? Now some sample questions already given here. You can see, you read out and solve these questions and just find the answers, and these answers You can just put in the comment box, right? Okay, logical instructions are the decision makers of embedded systems, unlocking smart control with simple logic, right? Thank you very much for listening me.